Okay, so sorry for the late start. So today I will start and finish chapter 9, which has to do with RSA public key cryptography. So the main thing to note that contrasts what I'm going to be talking about today with the other crypto systems that we talked about, the classical ones, is the following. So the classical crypto systems we discussed were all symmetric crypto systems. Okay, which I mentioned before. Symmetric crypto system meaning that the exact same info is needed to encrypt and decrypt. Okay, and so the sender and receiver must have the same info in the form of a key that is responsible for encrypting and decrypting. So there's a number of reasons why this is not so great. As I already mentioned before, there's the problem of communicating the key, right? So it's not as much of an issue if I can, directly hand off the key to a person to ensure that no one, intercepts it. But there's the circular problem of if I had a method to securely send the key in the first place, then I would have no reason to even need to use the crypto system to begin with, because the entire purpose is me trying to come up with a secure way of sending messages. So you might say, oh, well then symmetric crypto systems clearly we'd never use those. But that's not you can't quite say that, because there is a benefit to symmetric crypto systems, and it's that the current practical use of them, the symmetric crypto systems tend to be a lot faster, and so encrypting things in this way using a symmetric crypto system tends to be more efficient. And so that's a nice thing. Now, as I mentioned before, the symmetric crypto systems that are involved in this don't really have anything to do with number theory, and so we're not going to really talk about those. But they do have their purpose. So it's not just all asymmetric crypto systems or bust. So I already said the word. The RSA encryption algorithm is an example of an asymmetric crypto system. Okay. So in particular, not only is it asymmetric, meaning that the info needed to both encrypt and decrypt they're different, right? So the info needed to encrypt is different from the info needed to decrypt, okay? But also, it is an example of, just look at the words here, public key, of a public key crypto system. Okay, which is exactly what it sounds like. The key used to encrypt is actually publicly available. Okay, it could be published on your website. It could be sent out to every newspaper in the world. It could be completely public for all to see, so that anyone could encrypt using your public key. But the private info, the info that you keep hidden, is what is needed to decrypt, okay, the messages encrypted using this. So this has a number of benefits, obviously. So the first example that we'll do with this after I go through the setup, the example discussed in question is like online commerce, right? So suppose that you have, an online shop. You want to sell some item to people, and those people are going to be sending you credit card info, right? And the reason why this is a nice solution to this is, if you thought about trying to use a symmetric crypto system to do this, the problem is that the key used to encrypt any given say credit card number, right, would be shared. And so the problem was that since that key used to encrypt is the same key used to decrypt, anyone intercepting it, if they had the key necessary to encrypt credit card number, could decrypt any other credit card number or any other payment info encrypted using the same method. And so whereas if there was a way for my key to be public so that anyone could use it, but I have secret info that allows me to decrypt these messages, and if the process by which this happens is suitably difficult to, figure out my private info that allows me to decrypt, well, then I have a nice, robust encryption method. So this has a pretty interesting history. So this was actually originally developed, I believe it was developed by the by British intelligence agencies, and it was kept secret until a lot more recently. I think it was kept secret until like the 90s, but it was essentially discovered within only like a few years of this original British discovery that was kept secret. It was discovered in the late 70s. I think by 77 or 78, this method that I'm going to describe was entirely known. Okay, and so I'm going to read a problem before I set up this this process exactly to explain. So before I get into it, like what is, as I mentioned previously, the downside of public key crypto system is that it can be very expensive and time consuming to actually encrypt using this method. And so, as I mentioned, symmetric crypto systems can be more efficient and quicker in this. And so the idea here is you could use something like RSA, the asymmetric crypto system, to send a key in a secure way that would be used in a symmetric crypto system like the two previous ones, the DES or AES, would be used to send the data after that, having their key, having been securely sent. Anyway, so that's an application. But to give a specific example that I'll work through a related example here in a bit once I've stated the algorithm, here's the following. So let's say that Alice owns a bookstore, and in order to generate revenue, she's got to accept online orders. So Bob sees a book that he wants, but in order to purchase it, he has to send Alice's credit card number. He's concerned that if he does so, someone may intercept his communication with Alice's store and steal his number. But he knows that, in symmetric key crypto systems, the key used to encrypt is the same key used to decrypt. So if you want to send a secret message, you have to protect the encryption key and the decryption key because they're kind of the same thing, right? It's the same info. And since Alice ideally wants to have a lot of people with her encryption key, this causes an issue, right? Because that key is shared, and so someone with malevolent intent could use that key. So then this method of having a public key is the solution, right? So the idea is that you have a public key that can be accessed by anyone, and the secret info is hard to work out. Now, you may have heard previously that RSA public key cryptography relies on the fact that multiplying two gigantic prime numbers is trivial for a computer to do, but factoring a very large number that is the product of two very large primes is a very, very hard problem. So at the moment, that is a computationally infeasible problem to be able to factor gigantic numbers that are the products of, say, two primes. Being able to factor some huge number into its prime factors is a hard problem in general, and that is why this process works. And I'll address concerns that this might be a little bit subjective or time sensitive later. We'll talk about that later. So RSA is named after the three discoverers, co-discoverers, I should say, whose their last names spell out RSA. So that's where the name comes from. So there was, before that, I think a year before that, there was this paper by Diffie and Hellman. You'll hear those names again before the course is over. We'll discuss some things arising out of that. But anyway, before I do an example, I want to set up exactly how this public key cryptography system, this RSA setup, works. Okay, so here's the setup. So first, in that problem that I listed, which is you have Alice who wants her public key to be out there and able to be used to encrypt a ton of messages to be sent to her and then safely decrypted with secret info that only she possesses. Okay, so Alice chooses 2 primes. Okay, say P and Q. Now, practically speaking, for cryptographic applications, this P and Q would be very huge, say at least 100 digits long. Okay, for our handworked examples, they will obviously be smaller, just so that we can actually manage to write out stuff without everything taking a really long time. But the idea is that these in generally are going to be pretty big. Okay, and computes N, which is P times Q. Okay. Well, once you have N computed in this way, and of course, as I mentioned before, I'm just going to go ahead and keep a running tally of this as we go along. This step is very easy. This is computationally easy. Computer can multiply 2 gigantic numbers in no time, right? This doesn't take very much at all. Now, and in addition to computing this product, she computes phi of n. But because n is a product of P and Q are 2 gigantic primes. They are distinct, so they're relatively prime in this way. And so since they're relatively prime, n is a product of those things. Phi of n is phi of P times phi of Q, but they're prime. So this is just P minus 1 times Q minus 1. And so again, you're just multiplying 2 numbers together here. So computing, once you actually know this factorization of n, well then computing phi of n is easy. Okay, it's just another multiplication. Okay, so that's the first step. Second step, Alice chooses an E. This is the encryption key. Okay. So that the GCD of E and phi of n is 1. So E is relatively prime to phi of n. Okay. So this is going to be the public key. All right. Then Alice computes D, the decryption key, okay, with the property that E times D is congruent to 1 mod phi of n. Now, if it's not quite clear to you what's going on here, don't worry. We'll go over in detail why this is going to work out the way that it does. Okay, so Alice computes D, which is the decryption key, And she computes this by, she's already previously chosen E, so then she's computing the multiplicative inverse to E mod phi of n here, right? So this is a linear congruence that she can solve. Of course, practically, how is she going to do this? Well, you can think about that for a second, and we'll discuss it here in a few minutes. So then Alice makes N and E public and keeps D, P, and Q secret. Okay. As we'll see, and I'm going to sound a bit like a broken record because I'm going to repeat these things a lot, but as we'll see, the reason why D, P, and Q need to be secret. So obviously, D is the decryption key, so in whatever follows, hopefully knowing D alone is going to allow me to decrypt any message that I receive that uses the encryption key E, okay? And you might be able just intuitively to see what it is that is going on here, right? If E does something, whatever E is doing, the fact that D is a multiplicative inverse for E mod phi of n is heuristically, this is saying that D is undoing whatever E is doing, right? And we'll see exactly what we mean by that. You've actually already seen an example of this yesterday. So in yesterday's lecture, one of the examples I did actually covered this. It was an explicit example of this D undoing the process. But we'll see what's going on there. So it's obvious why, if you're thinking ahead to whatever process is going on, if D is really the decryption key, obviously that has to be secret. Why does P and Q have to be secret? So it turns out that if I know either P or Q, then factoring in completely becomes a lot easier. So if I knew N and E and either P or Q, I could find the other one. And once I know that, computing this decryption key is easy, right? Everything becomes easy after that. If I know what P and Q are, if I can factor in, this whole process falls apart. Okay, and so this entire process that I'm going to describe now after this setup really relies on N being hard to factor. Okay, if you could determine P and Q, everything here falls apart. Okay, so this entire process becomes trivial to break. Okay, in that case, and so I have public info. So the public info is N and E, and I have private info, which is D, P, and Q. Okay, and this is as good as I can do. As I said, if I make any of these things public, this whole thing falls apart. So how does the actual encryption method work? So this is the setup. So suppose that Alice has done this. Okay, so Alice has done this. She has chosen her two gigantic primes P and Q, multiplied them together to find N. Phi of n is easy to compute after that. She chose her E in this way. It turns out, I'm going to make a lot of, I'm going to say a lot of stuff about this. It turns out that the E chosen need not be gigantic. In fact, E could be chosen to be fairly small, and this is still a pretty secure process. So anyway, so she's chosen her E in this way, computed D as the thing that solves this linear congruence here, and then N and E are made public, D, P, and Q she keeps hidden. Okay, so that's the setup. Now, how do I encrypt with this? So if I'm Bob and I'm wanting to encrypt a message to send it to Alice for her to decrypt securely, how does RSA encryption work? Okay, so first, Bob looks up Alice's N and E, which are publicly available, so that's not too hard. Okay, so this is exactly the info that has been made public. All right. Secondly, Bob writes his message as m mod n. Okay, now you might immediately say, wait, say he has some text message. How does he encode that as a number m mod n? Well, he could agree upon some method of doing this with Alice. So for instance, even doing it in the way that we did it before, so making assigning a to be the numerical value. Well, you might not want to use 0 because then if a word begins with A, you would be dropping a digit. So you could let A be 01, B be 02, C be 03, and so on, all the way up to Z being 26. So you could do that, and in fact, you could tell everyone in the world you're doing that. Okay, because the process that follows is the secure bit. So even if they know how you're turning your text message into a number, they're not going to be actually able to figure out this number that you're using. Okay, in general. So that, however you encode this, doesn't matter too much, and that can be known to people. So then Bob computes C, which is this M, his message, raised to the encryption key. So that's exponentiated to this E mod n. Okay. And Bob sends C to Alice. Okay. So Bob doesn't tell anyone what his choice of M is. He could describe the process by which he turns a text message into an integer, but as long as he doesn't give them what M he's sending along, then the idea is once he transforms it to this C, we don't care if someone intercepts this C because this process is robust enough that they're not going to be able to figure out M from C, but Alice will be able to. Okay, and she does that via the following decryption method. So Alice receives C from Bob. Okay. And secondly, Alice computes M, which can be computed by taking the C and exponentiating it to the decryption key, mod n. Okay. And so that's the process. Now, there's a couple questions you have. One, you might have a question about why exponentiating C to the decryption key recovers M. We'll go over that. So I'll explain what's going on there. But what is this process simply? So whatever Bob encodes his message as M mod n, he exponentiates that to the encryption key and gets some number C out of it. So that C gets sent along. Alice takes the C, exponentiates the C to the decryption key, and that, according to this, what I'm writing here, should recover M. Okay? So that is the process. So that setup had to be done beforehand. There had to be a public key. So N and E had to be known. D, P, and Q are kept secret. But practically speaking, all that's needed to decrypt here is D, because you've used P and Q in your computation of D to begin with. Okay? So that is the process. That's how it works. So let's actually see this in action. So some of the numbers I'm going to use here, fairly big. Don't feel too bad if you can't do these multiplications and these computations off the top of your head. But at each step, I'm going to stop and explain, how it is I'm going to do some of these computations as a result. So For instance, like how I come up with D, right? How I compute D in the first place. So let's do an example, and let's move on from the bookstore example. So the problem set up here is Alice, realizing that she can't make money selling books, decides to become a spy. She needs to be able to communicate securely with the other spies in her network, so to do so, she chooses two primes, P and Q, multiplies them together to get her modulus N. So P here we'll say is, not going to even try to read this off nicely, this is 3598279. So 3,598,279, apparently that is prime. Q is another prime. It is 7,815,629. So I have two primes, P and Q. Let's stop for a second. You might have a question immediately that is, how do you find these primes? How would you go about finding these primes? Well, you might say, you know what, I'm going to just pull out my laptop or my phone or whatever my favorite, computational device of choice is, and I'm going to hit up the internet, and I'm going to use my favorite search engine, and I am going to type in list of the first, 20,000 primes, right? And I'm just going to see what comes up. Maybe I could even be smarter and say, give me a list of primes greater, or between, say, 500,000 and 5 million, right? You can probably get some results out of that. And so you do that. You pull up a list, and then you just pick some big primes that you like the looks of from your list. Now, there's a couple of things here. One, how do you know that the list is telling you the truth? How do you know that they're really prime? Well, you can make arguments about, well, I just take it on faith that these people wouldn't lie to me. If you say like, well, I could try to factor it myself, right? And when I fail to do so, I'll know that it's prime. Of course, maybe you even say, oh, I use Wilson's theorem, right? I use that corollary to Wilson's theorem to try to say whether or not this thing is prime. So we are going to discuss later, very briefly, in chapter 14, methods for, methods that you could use to, say, come up with your big primes that you're interested in using for these purposes. Okay, but for now, we'll just say we have been divinely inspired to write these out as primes. So if n is p times q here, I'm not going to actually multiply this out. I'm just going to copy what this is. So I'm just going to copy a bunch of digits here. So let's see, 281, reading from left to right, 281, 228, 137. 02491. So there it is. That's a big number. Okay, so there's n. N is huge. Okay. So then next we want to choose E that is relatively prime to phi of n, which is, I'm not going to write out what that is, but of course phi of n is just p minus 1 times q minus 1. Okay, so whatever that is, I'm not going to write that number out, but I want to choose an E that this works for. So it turns out that E equals 233 is such an E. Is it unique? No. There's a lot of choices you could make here. We're going to make 233 for this example. Okay, so E equals 233. is our choice. I'll mention this later. There are some E's that are nice and big and also convenient in a number of ways. So for instance, you might prefer to have an E that is close to being a power of 2. And the reason for that, of course, would be that if you had an E that was close to being a power of 2, then when you do this eventual exponentiation, when the person encrypting is doing the exponentiation, then what that means is that the process of doing the exponentiation is going to involve mostly squaring the number in question. So it's a bunch of squares and then some extra multiplications. We'll talk about that a bit later when I actually go through, how you practically compute these things. So we'll say that E is 233. That's our encryption key. Then we solve E times D is congruent to 1 mod P minus 1 times Q minus 1. Right? Or 233 times D is congruent to 1 mod P minus 1 Q minus 1. And when we solve this linear congruence mod this giant number, this gives me my decryption key D, which is fairly huge. I'm just going to, again, read from left to right. 275.193.086.77241. So this is our decryption key from solving this linear congruence. Okay, how? So in this step, let's quickly go through to make sure I know what I'm doing in each step. So I'm choosing 2 primes. How do I come up with that, out of the ether? Well, I've said we'll talk about later methods that you could use to come up with large primes. But for now, we'll say you just find a trustworthy list of large primes and you pick 2. Multiplying them, I don't need to explain what's going on there. You just multiply. You use your favorite computer and you multiply those 2 things together. So boom, multiply these 2 things. Then I'm looking for an E that's relatively prime to phi of n. Computing phi of n is again a multiplication. Picking a number that's relatively prime to this thing is not too hard. Tons of options that you could pick. This is just one that we just selected. So again, there's really nothing to explain up to now. Now I have to solve this linear congruence. How do I do this practically? So I solve this linear congruence by the extended Euclidean algorithm, right? Via the extended Euclidean algorithm. That's how we solve these things. Okay. So then we make N and E public and keep D, P, and Q private. Okay. All right. Okay, so now say that Bob wants to encrypt the plain text car. Okay. So how might he do that? Well, if you use the old thing that we did when we were talking about shift ciphers, so using that method is not so great because A is 0, so any word that starts with an A would start with a 0 and it would get dropped. So we would need this to rework this assignment of number values to these letters in a way that doesn't have any of the individual letters getting dropped. So to do that, we just say let A be 0, 1, let B be 0, 2, let C be 0, 3, and so on until Z is 26, right? So 2-digit numbers like that. Okay. Okay. Then Bob's choice of M is CAR, so that's 030118 would be R. Of course, this 0 in front, that's not how we do numbers. So this is congruent to 30,118 mod n, okay, that I'm not going to rewrite. Okay. Now you might say, wait, you've gotten something here that's slightly different. How would you know going backward? Bob could actually say, Bob could make public this method of encoding numbers. And doing this, since every letter is associated to a two-digit thing, when you get an M that doesn't have an even number of digits, you would know that a 0 has been dropped, in the first slot, right? So no big deal. This is not a big problem. So this is Bob's M. Okay? And so how does Bob encrypt this message and send it along to us or to Alice? Well, he needs to exponentiate this to the public encryption key, which is E. Okay? So Bob looks up the publicly available key, which is E. That is 233, and then he just computes that exponentiation. So I'm going to move on to the next sheet so that we have more room. Okay, so Bob computes his M to the E. So C is M to the E, which is congruent to 30,118 raised to the 233. Okay. And finds that this is congruent to, I'm just going to read off numbers from left to right, 21666 077 416 496 mod n. Okay. How would one go about computing this reasonably? So this is via modular exponentiation. So remember those the modular exponentiation. Oh, I'm not being able to spell here. Remember those modular exponentiation examples I did in the algorithm that you did to deal with those. That's exactly what we would do here. Right. Okay. This is where what I said earlier comes into play here, where if the E that you're raising this to is close to being a power of 2, then essentially to do this, you're just squaring a bunch. Right? You're squaring over and over again, reducing mod n, square, 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 reduce mod n, and then the last few multiplications you do would be what you need to fill out the rest, right? Of course, you can do that anyway. It's just that it's a lot more convenient if that exponent is close to being a power of 2. Okay. All right, so Bob computes this number. All right. So he sends along this number, right? So Bob sends C to Alice. Okay. So Alice decrypts by computing C to the D. So that, of course, is that really, really long thing that I'm not going to write. So that's C to my number D, which is also really long. So 27519 123.08677.241 mod n. Okay. And it turns out that this is congruent to 30,118 mod n. So again, via modular exponentiation. Okay. Thus, Alice has recovered the original m, right? Okay. Okay. And so, there's a few things that you might notice here. Okay, so I'll try to wrap them up in a list of comments about this process. The one thing that you might have the biggest question about is, how does this reversal happen, right? Why does exponentiating in this way reverse this process of encryption? So we will prove a proposition that explains exactly what's going on there. That is the thing that we've done an example of. We did an example of yesterday, actually. The quick answer to that is Euler's theorem. So Euler's theorem is the reason why this reversal works. Okay, so before I get to that, I was going to list out a few things. So some remarks. So the first remark is that P and Q should be large. Okay, so say more than 100 digits. The reasoning for this, of course, is to make this process as unfeasible to break as possible. Okay, that's the reason. Okay, and so finding them will be discussed later in chapter 14. I don't know how much time I'm going to devote to some discussion of things in chapter 14, so I might just briefly touch on it. But if you're interested into how you would actually find these, right? Your internet's broken. You got to find it on your own. Then chapter 14 is where this happens. Okay. So note that it turns out that factoring in is equivalent to computing phi of n. Okay. And so it turns out that this problem of factoring in is essentially as difficult or of a similar difficulty to computing phi of n, where this n is huge. Okay. All right. 2, E doesn't necessarily have to be huge. Okay. So E equals 3 has been used. Most commonly, E equals 65,537 has been used. So this might seem huge, but cryptographically speaking, this is not a very big number. So this has been used. What's nice about this is one off of a power of 2. So as I was saying earlier, the method of encrypting this is actually using this E is really easy because most of when you're computing these powers using modular exponentiation, most of the things that you're doing is just squaring them over and over. Okay, and then you have like one more multiplication by the base to do. All right. And the reason why this is nice, so E not having to be huge, what does that say intuitively? That's saying that the smaller E is allowed to be, the easier the process of encrypting is. Okay, and so being able to keep E relatively small means that encrypting is quick, right? Raising your message M to that exponent E is quicker if E is smaller. Okay. All right. So third remark. So we compute D via the extended Euclidean algorithm. Okay. All right. So we solve D times Z is congruent to 1 mod phi of n, which of course is P minus 1 times Q minus 1. Okay. Next, we will see later, again in chapter 14, that if someone knows E, D, and N, it is easy to factor in. Okay. i.e., finding D is equivalent to factoring in. Okay. So, why is this important to note? Because if we have faith that factoring in is a difficult problem in general, well, if it's equivalent to finding D, then that's saying that finding this D is a difficult problem. But finding the D is all that's required to be able to decrypt, right? So then what does this mean? It means that finding D via factoring in is hard. But if all I need is D to decrypt, then I should just abandon the hope of factoring in if factoring in is indeed difficult. So, i.e., attacks on RSA are likely to be easier if we focus on finding or on decrypting plain text without finding D. Right. Okay. So I will go through an example of how you might go about attacking RSA if you can do this if the message being sent is not too long. There's a way that you can go about this. It's actually there's a couple things I'll talk about, ways that you could go about trying to break this. It turns out these ways are very easily thwarted through one simple extra step. But this is basically telling you how you would attack this process. Basically, you're trying to decipher this without actually finding the D. Okay. And lastly, if Bob's message turns out to be bigger than N. So if Bob's message is larger than N, then it must be split up into blocks. Okay. Where each block is less than N. Okay. So we don't really care about the practical concerns here about sending messages larger than N or anything like that. We're not actually going to be doing the cryptography, right? We're just interested in the math side of things. So we're just going to assume that we don't have to do this. We're going to always assume that M is less than N so that we don't have to do this. Is just extra annoyance for us. Okay. So those are the main comments I wanted to make about this process. Now, big question. So as I mentioned, the big question is, why does this recovery trick work? Right? Why does exponentiating the ciphertext C to this D power that I found, why does that actually reverse the encryption? Okay, so why does C to the D recover the original message M? So quick answer is Euler's theorem. Okay, which is why we had to talk about Euler's theorem before we talked about this stuff. Okay, so that's the quick answer to why this reversal, this process is actually reversible, is because of Euler's theorem. The longer answer is a statement of a proposition. Okay, so the full answer is the following proposition that's a corollary of Euler's theorem. So full answer to the question is the following proposition. Okay, so here's what it looks like. Let N be a product of two primes, P and Q. So let it be the product of distinct primes. Okay, let D and E be positive integers satisfying D times E is congruent to 1 mod phi of N. Okay. Then, for all integers M, M to the E times D is congruent to M mod N. Another way, i.e., if C is congruent to M to the E mod N, then C to the D is congruent to M mod N. So this is literally the statement that last step in our RSA process, the decryption step, actually decrypts the message to give us M, which is what the person started with before they applied RSA encryption. Okay. So, as I mentioned before, this is entirely due to Euler's theorem. Okay. So, proof. Why does this work? So first, we'll deal with the case where m and n are relatively prime. Okay. There's some heuristic reasoning I can give for why this is the more obvious case, or why this is usually, this is the typical case, I should say. But we're gonna cover both cases anyway, so it doesn't matter. So anyway, when m and n are relatively prime, what does this allow us to say? Well, since E times D is congruent to 1 mod phi of n, we say E times D can be written as 1 plus k times phi of n for some integer k, which of course I can write as 1 plus k times, I could have just left this as I did up above, doesn't matter. So this is p minus 1 times q minus 1. All right. Now, but by Euler's theorem, m to the phi of n is congruent to 1 mod n. All right. Thus, m to the ed is congruent to m to the e. Oh, that's not what I wanted to write. I was just copying myself. This is, I want to write m to the 1 plus k times p minus 1 q minus 1, which I can write as m times m to the phi of n to the k. But m to the phi of n is congruent to 1 mod n, so this is m times 1 to the k mod n, so this is congruent to m mod n, which is exactly what I wanted to show. So this is easy to do in the case that I have GCD of m and n 1. Okay. All right. So this is the main reason. This really covers it, and of course it is absolutely 100% due to Euler's theorem. Okay. Now there's some bookkeeping I have to do in the case that I don't have m and n relatively prime, but it's really not a big deal. But I will do it just for completion's sake. So I will continue the proof. So this is the case when the GCD of m and n is bigger than 1. All right, so this will exhaust all of the cases. All right. Okay. So in this case, GCD of m and n has really 3 options here. It's either p, q, or p times q, which is n, right? Why? Well, we know that n is p times q, right? So we already know what the divisors of n are, right? Not a whole lot of options here. So here's my list of possible options for this GCD if it's not 1. Okay, so I'm going to go through each of these subcases. So case when GCD of m and n is equal to PQ. Okay. Well, this case isn't too bad, right? So, i.e., in this case, n divides m. Why? Well, PQ is equal to n. GCD of m and n being equal to n means n is a common divisor of m and n, so by definition, n divides m, right? i.e., m is congruent to 0 mod n. Well, that's convenient. Thus, m to the ed is congruent to 0 to the ed, which is, of course, congruent to 0, but that's congruent to m mod n. So I'm done in that case, right? That's exactly what I'm trying to show. Okay, so then I have another case. So let's do the case when the GCD of m and n is p. Turns out this is all I need to do because the case when it's equal to q is going to be totally symmetric in argumentation, so swapping p and q is going to give me the completed proof here. So if GCD of m and n is p, so p is common divisor of m and n, so i.e. in particular, p divides m. So m is congruent to 0 mod p. Okay. Thus, m to the ed is congruent to 0 to the ed, which is 0, which is congruent to m mod p. Now, I'm not done there because, of course, I want to show this mod n, not mod p. So how does this help me? Note in this case, p divides m, but q, the other prime factor of n, doesn't divide m in this case. So q does not divide m. Thus, by Fermat's Little theorem, m to the q minus 1 is congruent to 1 mod q. Okay. Thus, m to the ed is congruent to m to the 1 plus k times q minus 1 times p minus 1, which is congruent to m times m to the q minus 1 times k, or to the k times p minus 1, which of course is congruent to m times 1 to the k times p minus 1, which is congruent to m mod q. Okay. So what have we shown here? So we have shown that m to the ed is congruent to m mod p, but also m to the ed is congruent to m mod q. Thus, m to the ed is congruent to m mod p, and m to the ed is congruent to m mod q. Rewriting this in terms of divisibility, what does this mean? This means that p divides m to the ed minus m, and also q divides m to the ed minus m. Right? But what does this mean? Right? This means that pq divides m to the ed minus m, or that M to the ED is congruent to M mod PQ. But PQ is in. This is in. So we're done. The case of GCD MN equal to Q is similar. So we're done. In any case, M to the ED is congruent to M mod N. Okay. Okay. So that gives us a solid proof to understand what it is that's actually going on that allows us to encrypt and decrypt using this system. Okay. So, what is left to say here? I mentioned that there were some potential attacks that we could discuss about concerned with what happens if the message that you're sending is encoded in few enough digits that one could actually exhaust the possible ciphertexts resulting from that encryption and actually figure out all the needed quantities from that. So I'll give an example of that in just a second, but the first thing I wanted to say is note, right? Since it turns out that knowing D, or being able to figure out D, is computationally equivalent to factoring in so we'll see this in chapter 14. The entire security of this process relies on factoring in being difficult. Okay. So maybe I should underline that, since this is kind of the entire point of this algorithm. So factoring in is needed. This needs to be very difficult in order for this process to have any security at all. Okay. So the question is it difficult, right? So currently, factoring large N is, going to use scare quotes again, computationally infeasible. Okay. So some alarm bells might be ringing in your head where you ask, what does that mean, right? What does it mean? Because I didn't say that it's impossible. I didn't say that it would be guaranteed to take too long to do. It's just that it's right now currently computationally infeasible. What this means is that it takes a ridiculously long time given current computational abilities, right? So what this means is that this process takes a very long time in general using current computational methods. Maybe I shouldn't just say methods, but technology, because it's not necessarily just a question of methods. It's also the technology itself. So the question becomes then, okay, so hypothetically, right, if I had some ridiculously powerful computer from the future that was maybe a quantum computer or something else of that nature, I could break this RSA encryption. I could take this problem of factoring in being difficult and make it something that's a lot easier. And the answer to that is yeah, that's possible. So it's possible that breakthroughs in computing could lead to this process not being nearly as secure. So in the near future, this doesn't seem too likely. But when it comes to making broad overarching statements about computational abilities, it's very easy to be very wrong. Speaking like right before a major shift in technological abilities. So I'm not going to make any grand statements about RSA will never be completely broken or anything, because it's just not that possible to know whether or not that's going to be the case. But right now, what can definitely be said is that using current computational tech, this is an infeasible problem. This takes way too long for a supposed attacker to find D in this way. Okay, so a potential attack that could bypass this in some simple cases relies on listing out some values and exhausting possibilities. This can't be done when the M in question is big enough. But when M is small enough, this can be done with some effort. So I will, rather than go into this process now where I don't quite have enough time to finish, I'll save it and do that tomorrow. So tomorrow I'll go over this attack and finish up RSA algorithm stuff with an application to digital signatures. And then we'll be moving on. We're going to skip chapter 10, so we're going to move directly on to chapter 11 after that. And I believe that's more or less it. So we've pretty much finished chapter 9, so we'll be moving on to chapter 11 starting tomorrow, and yeah, starting into next week. So I hope to, by the end of next week, maybe start a discussion of quadratic reciprocity. Homework 4 is, so I decided not to post it because I decided what I was going to do is make, homework 4 is going to be very short. It's going to be from chapters 7 and 8. It's going to be really short, and it's only going to be odd problems from the textbook so that you have some guidance there. It's going to be due at the same time as your exam, so it's going to be due on Monday. Same deal as last time. I'll post your exam 2 during the afternoon tomorrow. And let you know when I do that. And again, same deal as last time. It'll be due on Monday. And so your exam 2 will cover everything that we've covered since exam 1. So all the material from the last 2 weeks. Also, and I haven't done it yet, I'm going to clean up the syllabus page again and upload all the lectures in a nice format like I did before the last exam, and finish putting all these lectures into the playlist that I previously made. So you'll have all the lectures in one nice playlist. I'll have accurate descriptions of every lecture, and I'm going to put that on the course syllabus too on Elms. So yeah, I'll post homework 4 soon. I know I said I was going to do it a couple days ago, but I decided rather than giving you a homework of the same length that I'd given you for the last 3 times, I was going to give you a shorter homework with only odd problems in case you needed some guidance from the back of the book on how to do some of these things. Office hours still tomorrow as usual, so you can swing by if you have questions either about the homework I assign later or any of the material in general, and then I'll post your exam after the office hours. So that's yeah. So I did do office hours on Monday. My original plan was to just do office hours tomorrow as normal, but maybe it does make sense to have office hours on Monday instead, since you'll have had that weekend to have a look at the exam. So if you had any questions about that, you can ask me. So maybe I will move office hours to Monday. I'll put out an announcement tomorrow, make sure nobody is waiting around for office hours. I think it probably makes more sense to do office hours on Monday. So yeah, I will do that. So yeah, I'll put up announcements for all the relevant info and stuff, and I will see you all tomorrow. So yeah, I think that's pretty much it.